This is the lab technique video for the acids lab. First, after removing the electrode from its solution that it's stored in, we rinse off the probe. We make sure to hit the electrode on the end and to properly rinse it off. Next, we place it into the first buffer solution. The first buffer solution has a pH of 7.00. So you go into the Calibrate Options menu, select 2-point calibration, and change the first pH to 7.00, as I'm doing in this video. Next, we remove the electrode or the probe from the solution, rinse it off again with water to make sure that none of the first buffer stays on it, and then place it in the second buffer solution with a pH of 4.00. Once again, I change the second pH in the calibrations menu to 4.00, let it stabilize for a little bit, and then remove it. Now our pHs have been successfully calibrated. We rinse it off again, and we begin to take the pH of our first solution. In this case, our solution is apple juice. We place the probe in, making sure not to stir it, and then read out the pH. You can see in the video that the pH reads 3.53. This is how you take the pH and calibrate for any solution. Strong acids dissociate completely into ions. In the beaker on the left, the hydrochloric acid is dissociating into H3O plus ions and chloride ions. On the beaker on the right, which is a weak acid, it dissociates only partially into fluoride ions and H3O plus ions. Basically, strong acids completely dissociate, whereas weak acids do not dissociate completely. This leads to a pH lower in favor of the strong acids. The strong acids have a lower pH, whereas the weak acids have slightly higher pH, although both pHs are still less than 7. As established previously, weak acids only partially ionize. Remember, when we add water to, for example, acetic acid, it'll only partially ionize into acetate and hydronium ions. So, one thing that's important to notice is to reduce the effect of the weak acid, which means to increase the weak acid's dissociation, we add more water, which, due to Le Chatelier's principle, shifts the equation towards the right, and means that we're going to have more H pluses coming out of the weak acid, or the weak acid will dissociate to a greater extent. That being said, since we're also diluting the equation, the pH will still increase, because the dilution will overpower the increased effects of the dissociation of the weak acid. This table is a detailed reading of the pH values from the pH meter of the various solutions measured in lab. The juices are slightly acidic and have acidic pHs. Sodium and ammonium hydroxide are basic and therefore have basic pHs. Acetic acid is a weak acid, and you can see that the pH is low, as you would expect. And hydrochloric acid is a strong acid, and you can see that the pH is very low, as you would expect. The actual pH values given from the pH meter were recorded earlier in the technique portion of the lab and are visible in that section of our video, which is when I was calibrating and then measuring the pH of the orange juice.